Hello? Yeah.
We did a bit, yeah.
I can go around.
Okay, so let's continue with the last talk of the day. Still on flat space physics from ICTP.
All right, thank you very much, everybody, for coming. And of course, thank you to the organizers for inviting me. It has actually been great to be here. I've learned a lot of new things that I didn't know about before. The main reason being that I'm not the kind of person that actually works on the S-matrix Bootstrap or anything related to that. So today I'm going to present some work that I have done that I think might be related to the S-matrix Bootstrap. But my perspective is a little bit different. I come from ADS-CFT and holography, and I have landed here by trying to study, trying is the keyword here, flat space holography. So let me explain a little bit the logic that I'm following. So what I would like to understand is whether or not one can obtain a microscopic description of some theory of physics in an asymptotically flat geometry. And so I would like to apply the holographic principle to such geometry. So let me draw it. This would be Minkowski space. And in order to apply the holographic principle, the first thing I need to do is to choose a boundary. And some people believe that the relevant boundary to consider is the asymptotic null infinity boundary, which is this one, this asymptotic past and future null infinity. And I think that at least part of the boundary should be asymptotic null infinity. So that would be the first question: what is the boundary of our spacetime? And I'm going to claim for now that that is a reasonable boundary. The next question that you should ask if you're trying to apply the holographic principle is a question about symmetries. So you need to identify what are the relevant symmetries of this theory. As in ADS-CFT, what we could do is to try to find for all the asymptotic gauge transformations or all the asymptotic diffeomorphisms that leave my metric or my gauge fields or my matter completely invariant, except at the asymptotic null infinity where I fixed everything to be empty Minkowski space. If you do this, there is some famous work by Bondi, Meshner, and Sachs in which they find that the relevant symmetry should be BMS symmetry. So some people expected to find Poincaré symmetry, but of course that is enlarged. Poincaré symmetry is the symmetry of the full spacetime. If you allow this spacetime to change somewhere deep in the bulk of Minkowski spacetime, it's not unreasonable to see how the group increases to something bigger, which is the BMS group. And the BMS group, just in case you guys don't know, is a generalization to the Poincaré group. It has, apart from translations and Lorentz transformations, it has super translations and super rotations. And so it is tempting to now claim that there could be some kind of theory living here. I don't know how this theory looked like, that is BMS invariant, and that knowledge of this theory completely replaces knowledge of the theory in flat spacetime. So Okay, I mean, this super translation, super rotation, I mean, in principle, so, this kind of group can be defined for higher dimensions. So they can be defined for BMS. So there's BMS3, there's BMS4, then there's BMS5, 6, or 7. But it's not clear that those groups are actually the asymptotic symmetries of Minkowski spacetime in 5, 6, 7 dimensions. But at least for 3 and 4, it's clear that, that this group exists and it's understood. Okay. All right, so okay, so in principle, it would be great if you gave me a BMS invariant theory and then computing correlators of operators in this theory gave me the observables of the flat spacetime theory. And in a sense, that would be the holographic dictionary. So in ADS-CFT, the statement of the holographic dictionary would be that if I compute some conformal correlator of boundary operators, what this is computing is some field configuration in ADS spacetime with the right asymptotic boundary conditions. So here, I want to regard the holographic dictionary in flat space as a statement that if I compute a correlator in a BMS invariant theory, then I should be obtaining the S matrix. So to me, coming from this logic, the S matrix is a BMS invariant object that one could in principle compute from a microscopic theory that is BMS invariant. Okay. However, okay, the story ends here because I don't know what these theories look like. I don't know if they're quantum field theories. I don't know if they're quantum mechanical theories. I don't know anything about them. And so I need to find, if I want to understand this spacetime microscopically, I have to do something different. So instead of applying the holographic principle directly, I'm going to apply it indirectly using ADS-CFT. So let me explain a little bit the concept of an indirect approach to holography. Yep.
I always have the question here: what kind of scattering amplitudes are you trying? Are you finding here? Should I not worry about the infrared divergence?
Yes, I will talk about this. In principle, for the purpose of this talk, the kind of S matrix that I'm going to study is going to be IR divergent, and it's going to rely on a definition of an asymptotic Fock space with respect to some free Hamiltonian. But I hope it will be clear throughout this talk that what I do can be modified to account for the IR divergences, and you can do more work to get IR finite answers. And this will lead us to the definition of Fatef-Coolidge states from the perspective of ADS-CFT. But let me mention that again a bit later.
You are expecting some string theory in this one?
Yes, but for now, okay, I'm going to study the semi-classical limit, where I will consider quantum field theories propagating in asymptotically Minkowski geometries. Okay, I'm not going to consider string theory. All right, so here's the idea for indirect holography. So let me draw ADS spacetime, or at least a time-slice of ADS spacetime. It looks like a disk. At the boundary of this disk, we would have the CFT, whose knowledge replaces the knowledge of the ADS geometry. Now, in the middle here, the lengths are pretty small, so I can fit a certain amount of squares, let's say. As I approach the boundary, the lengths start increasing, so I can fit more squares, so squares are a little bit smaller. And I guess as I approach the boundary, lengths start diverging, and I fit less squares here. And the fact that we see these squares kind of changing size is a statement about the fact that ADS is a curved geometry, and there is some ADS length scale that measures how much the size of the square changes as you move along this disk. And now imagine the following. Imagine that we have a physicist that lives somewhere here, some kind of being that studies physics somewhere there, but that this person does not have access to the physics above the ADS length scale. So whatever happens around here, this physicist has no access to it. So if this physicist does some experiment here, he will basically experiment flat spacetime physics because effectively speaking, the spacetime here is flat. So in this region right here, what this observer would see is some flat arrangement of squares. And so in principle, if this guy did experiments, he could find the same answers that we find in LHC or in LIGO, even if you let gravity propagate, or even like he could see asymptotically flat black holes and see them with the Event Horizon Telescope or something like that. So all of these rich physics that we see in the real world are somehow encoded in this region of ADS spacetime. So maybe it's not crazy to believe that information in the conformal field theory here contains information about flat spacetime physics. I think this is a very trivial statement, but the hard question is how do we extract this knowledge from the conformal field theory. Okay, so I think if you had more knowledge and analytical power than me, you would probably try to attack this question in the sense of, okay, let's find how can I deform conformal field theories such that these conformal field theories become the holographic duals of flat spacetimes, and so at the level of the theory, I would know exactly what the holographic principle tells me. But because I don't have that power, I'm going to only worry about how to extract the observables that live in flat spacetime from the observables of the conformal field theory. Okay, so let's talk about that. Observables. Okay, so first let's identify what kind of observables I can have in any of these theories. In a conformal field theory, the kind of observables that I can measure are conformal field theory correlators. So say that my conformal field theory lives there, and say that my conformal field theory is in some state that I call psi. Then I can insert some amount of local operators, like these guys, and I can compute correlation functions. So I can compute something like this. And the freedom that I have is what state my CFT is in and what operators I insert in this correlator. However, the kind of observables that I have in flat spacetime are in principle the S matrices. So let me draw this as a Minkowski spacetime, and I can have some asymptotic states coming in that are massless, and some massive ones even, that they interact in some crazy way right here, and then they come out as asymptotic out states, massless or massive or whatever. So here the flat observables would just be this S matrix that I will define as an overlap between in and some S matrix operator and out. So the question that I would like to attack today is, how do I take this conformal correlator and turn it into an S matrix, which is something that we have already heard about today. I'm going to try to give a first principles derivation of a possible formula to relate the S matrix to this correlator. Now let me give you a little bit of history before I tell you how I think of this issue. There was, initially there was some papers where they considered S matrices involving only external massless particles. The way they did so is because the mass of a field in ADS, the formula that it obeys is something like this. So if you take the, let me write R. If you take the large radius of ADS limit, which is this value R, you can turn the mass to 0 if this object scales, it doesn't scale with the ADS length scale. So if your conformal dimension is of order 1, it doesn't scale with the ADS radius, you can in principle find the S matrix associated to massless particles. And Joao had a conjecture for how to extract the S matrix from a conformal correlator. Here, the conformal correlator was written in terms of Mellin amplitudes, and then in the end you end up getting some crazy integral of some Mellin parameter over some Mellin amplitude evaluated at a particular value of the Mellin variables. This conjecture was proven by first principles by Fitzpatrick and Kaplan, and morally speaking, what they showed was the following, is that if you consider some ADS geometry, let me draw it here by a cylinder, and inside this ADS geometry, you consider some flat space scattering region. This flat space scattering region has the property that as I turn the ADS radius to infinity, this geometry becomes flat. Then they could insert an operator somewhere here at pi over 2. Let's say this is pi over 2, and this is minus pi over 2 in global time. They could insert some smeared operator somewhere here at this value of pi over 2 in global time. And that corresponds to some massless particle that propagates inwards into de Sitter spacetime and turns into a scattering state here with null momentum. And so if you compute a correlation function of operators like this that are located at pi over 2 if they are out states or minus pi over 2 if they're in states, you can derive this formula, okay? Another formula that was proposed actually, I think, last year, also by Joao and company, is that if your particles are all massive, so if all your conformal dimensions scale with R, such that the mass of your ADS field stays finite in the large R limit, then you find the following formula, which is just the Mellin amplitude evaluated at a particular value of the Mellin variables given by this formula right here. And what I'm going to try to convince you today is that all of these formulas just come from the same master formula that you can take to all of these special cases in the appropriate limit. All right. So how are we going to do that? The first thing we need to do is to understand how the different states in my conformal field theory turn into the different asymptotically Minkowski geometries. So first I'm going to convince you that depending on what state you choose in your conformal field theory, you will be studying scattering in a different geometry. And the next thing that I'm going to convince you of is that with these operators, you can build the scattering states. All right. So let me start with the issue of conformal field theory states. So how do we turn conformal field theory states into different asymptotically Minkowski geometries? And let me start explaining this with a very trivial example. So say we start with a conformal field theory state that is just the vacuum of my conformal field theory. Using ADS-CFT, this state is related to a particular ADS geometry. So I'm using ADS-CFT here. And the ADS geometry is global ADS, that I will draw here like a cylinder. And the metric of ADS, I will take it to be the usual one. Let me write it down explicitly so that the limit is clear. So this is the global time, this is the holographic direction rho, and then there is some solid angle. Okay, now the statement that I'm going to make is that if I study some region here in the center of global ADS, so this region right here, parameterized by a value of global time that is small with respect to the ADS radius, so the value of global time would be T over R when R is tend to infinity, and then rho is also small compared to the ADS radius, then as I take the large radius of ADS limit, then this geometry will basically turn into Minkowski space. And indeed, you can see this very explicitly in the metric. This metric, when we take the large radius of ADS limit, will simply turn into the usual minus dt square plus dr square plus r square d theta, which is simply Minkowski space in cylindrical coordinates. So okay, I hope it's clear. It is very trivial that if I compute correlators in a conformal field theory vacuum, that should be related somehow to S-matrix amplitudes in pure Minkowski space. Now, I guess it's not too crazy to believe that there's a class of conformal field theory states, let me call them psi, that through ADS-CFT are related to ADS geometries that will be asymptotically ADS, always, right? That's the case for conformal field theory states, but that are different from they're different from global ADS in regions smaller than the ADS length scale. So they can have here something that in the geometry can be back reacted, but in a distance that is not bigger than the ADS length scale. If that happens, and I define this scattering region somewhere there, what I will find is that my Minkowski spacetime is now only asymptotically Minkowski, but that inside this region I have some non-trivial back reaction. To be clear, let me give an example. I mean, in principle, you could consider some conformal field theory state that corresponds to a star in ADS, and the radius of this star is not of the order of the ADS length scale. So when you turn the ADS length scale to infinity, you zoom in close to the star, and then the geometry next to the star is heavily back reacted by the star, but asymptotically far away from it, it's just flat. An example that I will use later, just to be very clear, will be a two-dimensional CFT example. Is this state that I will call alpha. This is a 2D CFT. That is known as a conical deficit state that you can generate by acting on the vacuum of the conformal field theory with a heavy operator. So this is an operator whose conformal dimension scales with c, something like c times 1 minus alpha square over 4, something like that. If alpha goes to 1, this operator disappears and you just get the vacuum. So when alpha is equal to 1, this becomes the vacuum state. But when alpha is non-trivial, then this state is a non-trivial state of the conformal field theory. Through ADS-CFT, though, this state is dual to a conical deficit geometry in ADS. So it's something that has a deficit right here. And you can sort of understand this as the back-reacted asymptotically ADS geometry in the presence of an idealized string, a cosmic string, an idealized cosmic string. And if you take the flat limit, so if you take the r goes to infinity, then this will just become asymptotically flat spacetime in 3 dimensions, but now there's some idealized cosmic string somewhere here in the center of your Minkowski spacetime. And in principle, it should be possible if we have a map between scattering amplitudes and conformal field theory correlation functions to study scattering on this conical deficit flat geometry from the perspective of CFT correlators. How does it appear? I mean, you can think of it like you can think of this operator being located at a place of the boundary up here, like at the top of the cylinder, and then the dual field associated to this operator is so heavy that it backreacts your geometry, but only on a geodesic, and that geodesic creates a conical deficit. It's like a particle geometry. Was that sorry? How do you see it in Minkowski space? Oh, holographically, I have no idea. I can only write the metric. Oh, do you want me to write the metric? So I mean, all I can do is, from this conformal field theory state, I can reason that there is an ADS geometry dual to that state, and then I can take the line element of that geometry and take the flat limit. And that will spit out some geometry that only looks flat if I take the null direction to be large, but that close to the finite time region, it looks like there is some singularity at the origin, which corresponds to the cosmic string. This will be, this will be clear later with the example. Yeah. Okay, so I have told you, I hope I have convinced you that there's a class of CFT states and that you can associate to each of those states an asymptotically flat geometry. So now let me talk about scattering states, which I think is the most important thing to talk about.
Before you erase this, the little square that you draw there,
Here, yeah.
tell you that the boundary theory is local, I guess, but there it won't be local.
That's right. There is something, okay, so as I said, I am only taking this flat limit at the level of the observables. How to take this flat limit at the level of the theory, like how to take a conformal field theory and make it be a BMS theory, I have no idea how that works. And I agree that this might not be a local theory. Yeah, it could be some gauge theories. I mean, I don't know. Some people have some ideas about this, but I would rather not risk with any comment. All right, so before I mention how to build the scattering states, we need to define what we mean with a scattering state. And there was very wonderful talks on Tuesday about this concerning IR divergences and what is the proper definition of the S matrix. And from my perspective, it kind of all boils down to how to define the scattering state. So let me make an argument here. So let me draw this as time. And there is some region of time that I'm going to call early. And some region of time that I'm going to call late. And of course, time here goes to plus infinity, and here time goes to minus infinity. And then there's some finite time dynamics here. Now, what happens is that when particles are in this region of finite time, they can interact in a very non-trivial way. So here there's some crazy interaction that is mediated by some interaction Hamiltonian. But as time is early or late, we assume that particles are very far away from each other. And so in principle, they don't interact that much as the interacting Hamiltonian would tell you. So in principle, here in these regions, there is some asymptotic Hamiltonian that is a good faith approximation to the interacting Hamiltonian when the particles are very far away from each other. Now, for the purpose of what I'm talking about today, I will consider the asymptotic Hamiltonian to be free. And the speakers on Tuesday made it perfectly clear that this is a mistake, because if you do this, you're defining S matrices that have IR divergences and have a lot of problems. But this is what I will do for now. This is what was done today in the morning too. And in principle, this should correspond to scattering states that are Fock states. But something to keep in mind for later is that, for example, when we mentioned Fatev-Coolidge states, or better versions of these guys, the story here was that the asymptotic Hamiltonian was not really free, but that it included some kind of long wavelength interactions with gauge fields, gravity, et cetera, et cetera. So later, I will try to convince you that this can be done in the discussion that I'm about to show you. Okay, but for now, all that the statement to remember is I'm building S matrices concerning Fock states, And my theory, just for the purpose of building scattering states, the theory is free, okay? So for the purpose of building scattering states, let me talk about free quantum field theory in anti-de Sitter spacetime. And I'm gonna try to build a scattering states using that free quantum field theory. All right, so let me draw ADS again in the cylinder. This is ADS. And as I said before, I'm going to study some person that lives here in this scattering region that turns flat in the large R limit. This is minus pi over 2, and this is plus pi over 2. And now I am going to try to build a scattering state somewhere here. In order to do this, I'm going to study a local quantum field, a local operator that I'm going to call phi of x, that lives somewhere in this scattering region and that is free. So I want to understand what phi of x is. Now, in ADS-CFT, we have all of this technology about how to reconstruct local bulk operators in the bulk of our anti-de Sitter geometry as an operator at the boundary. One of the approaches to reconstruct these operators in the case of free fields is known as global HKLL. And the reconstruction looks like this. So there is an integral over the boundary of some kernel that depends on x, which is the location of the operator, and the point y at the boundary, and then some operator of a given conformal dimension at the point y. And this formula is only true if this field is free. If it's not free, this formula has to be modified. All right, and for the case, so here the operator will have conformal dimension r times m if you want some massive field. Otherwise, you can consider some operation or some operator with conformal dimension of order 1. All right, but now, as of now, I mean, this formula is just some local bulk operator living in this scattering region. I need to build a scattering state out of it. But that just means that I need to build some operator in momentum space, not in position space. So I will define the operator phi of p. So yeah, we'll define the operator phi of p as some Fourier transform. Put d. As some Fourier transform of this local operator here that in turn is some reconstruction over the boundary. Well, before I forget, let me point something important out, and is that the region that we integrate here in the boundary is the region that is space-like separated from the bulk point. So I guess in this picture that I drew right here, the boundary region would be something like this. So this is some light rays coming up to the boundary, and all of this region of the boundary that is space-like separated from the operator is this region right here. But now I'm taking this operator and I'm Fourier transforming with respect to the Minkowski space coordinates. So this point x lives in this scattering region right here. And of course, because we're taking because we want to end up in flat space, we need to take a limit when r goes to infinity of this expression. So I'll put the limit right here. All right. Now, this kernel is known. This kernel you can find in the literature is the Hkl kernel. And performing a Fourier, I forgot the e to the IPX. So this kernel is known. You can write it down explicitly. You can do a Fourier transform of that kernel, and then you can further take the limit when r goes to infinity. And what you will find is that this operator is essentially a bit of a smearing. So let me explain this t a little in a bit. So it's a little bit of a smearing with a frequency of the operator, this operator that we had right here, but in a very particular point of the conformal field theory. The point is that global time is some function of the momenta, which is this inverse sine of omega over k. And then the angle at which is located is the angle of the momenta, so k hat. All right, so let me draw this in this picture. What's happening is that, but before I do so, notice the following, and is that the sine, the inverse sine of omega over k is actually not a real number, right? Because omega over k is greater than 1. So the arc sine of something bigger than 1 is some complex number. And you can actually write this as pi over 2 plus I times something that depends on omega over and k. So what's going on here is that the point where we have to put this operator is a point in the boundary that is at a value of pi over 2 in global time, and then some complex number. So and some imaginary number. So we need to create a Euclidean continuation of our boundary, which I will draw here as a half sphere. There's many ways to draw this. You can draw an infinite cylinder too, or whatever. But here I will choose a half sphere. And then the operator is located somewhere at pi over 2 plus some value of the half sphere. So let's say here. So this is where my operator is located. And I'm further smearing it over some small window of global time. So I'm integrating this guy over some small window of global time. All right, so this looks pretty weird for now. Yeah.
I'm a little bit, can you be a bit more precise? So you're integrating over Minkowski, but before taking the R to infinity limit, you don't really have a Minkowski.
Right. So first, I mean, there is a limit here. So first, what you can do is you can write this kernel in the large R limit, because you're replacing this ADS point by the point in the scattering region.
So you're taking the limit inside the integral?
Yes, I'm taking the limit inside the integral. Okay. And then I'm performing this e to the IPX, and you will get some, if you do this with the explicit kernel, you will get that delta function. There are some other ways to argue this, right? The way to argue is that the Hkl kernel has to obey the equations of motion in the bulk. If I take x to be in the scattering region, it means that it's solving the flat scattering, the flat equations of motion, which means that this object has to go like e to the IPX, basically, or e to IQX or whatever. But also this kernel has to be invariant under ADS isometries, so it can only depend on the ADS invariant distance. And the only way that fact is compatible with this kind of shape is if the point y is located at a very particular point in the boundary, which is this guy. Oh, and by the way, there's a plus t over L right here, t over R. Yeah, sorry, yeah, there's some smearing over global time, which I drew with this arrow right here.
This smearing is from minus infinity to infinity.
Yeah, what I mean is that...
In which sense it localizes in some way?
Exactly, it's localized with respect to the ADS length scale, but because you're taking this limit, you're creating this hierarchy between things that are ADS length scale or not, so you have to integrate over the length scale that is not of the order of the ADS radius. This is similar, I mean, this is also done in this work by Fitzpatrick and Kaplan. They also have to insert some small window of time here and integrate over that.
This is done by introducing some weight packets.
Yeah, exactly. So say now that omega is k. So let me use another color. So say now that omega equals k. Exactly, that means massless particle. And the arc sine of omega over k is pi over 2 in that case. So this complex thing goes away. And basically, you're moving this operator close to the boundary. So in the case of massless operators, you would have to put the operator here and integrate over a small window of global time that effectively creates a wave packet that propagates down into the scattering region. So what I want to say with this is that this approach in the massless limit effectively is the Fitzpatrick-Kaplan proof of Joao's expression for the S matrix. Okay. All right, but again, this is a bit more general because this operator can have omega not equal k, and you simply have to insert it at some non-trivial value of complex global time. And one way to think about this too is that, okay, in the case of massless particles, it's very easy to create a scattering state because massless particles reach the boundary of ADS. If you think of a massless particle propagating here in your flat spacetime and you let time run, that particle is going to exit the scattering region at some point and it's just going to reach the boundary at a particular location, and you can just think of an operator living at that point. With massive particles, that's not the case because massive particles follow trajectories that are time-like, but a way you can think of it is that that trajectory somehow hits a complex value of the Lorentzian boundary.
One thing I didn't understand, so from HKLL, you got the support, so the integral on the boundary was on the space-like region.
That's right.
Suddenly you're showing there's this complexification. What happened?
There is some kind of analytical continuation going on there. It's simply, if you do this kind of limit, you will just get 0 unless tau has some complex value. So I agree that it's a little bit fishy that the integration control, the integration regime was just a space-like points, but I guess I'm okay with it because this is also space-like separated from this region. So so I will not complain.
To verify against this.
Well, let me just mention one more detail about this. Another way we could think about it is that we're performing this integral with a saddle point approximation, and saddles are allowed to be complex, right? I mean, even if the saddle doesn't make sense physically, it's just capturing that in the value of that integral somehow.
So that's how you go from this to the last line. So you have d-dimensional
Yeah.
integral and then you
Exactly.
saddle point.
You can think of it as a saddle point, yeah.
And just to make sure, so the saddle point exists without introducing of any extra weight packet. Right? Just this integral.
Exactly. Just this integral will give you the saddle, the existence of the saddle. That's right. Effectively speaking, okay. Well, let me mention something now about these saddle points. So now, okay, I have told you how you can take some state in a conformal field theory, and depending on what state you choose, you will end up in a different asymptotically Minkowski geometry. And I have also told you how you can, in principle, reconstruct the scattering states associated to free particles using operators in the conformal field theory. So now let's put all of this together into a single formula. So the formula is simply that the S matrix associated to this process, and it's a process that involves some momenta pi, is some limit when where the radius of ADS goes to infinity of some normalization constant that I won't bother you with, but you have to take care of it, and then some product of integrals that come from these time smearings. Let me get rid of this line. So there is this kind of product of integrals here of different global times. And then the conformal correlator evaluated in this state psi and then operators located at particular points, where these points, so say for example xi, is parameterized by a complex value of global time something like this, plus d over L. And then some angle in the Euclidean half sphere that corresponds to the angle where momentum is pointing. Now, actually, when you do this kind of logic, there's two solutions. One of the one that I'm writing here would be the ones for the out states. But in principle, you could also build in state by scattering, by placing operators down here at minus pi over 2. So you could attach a Euclidean half sphere here, place an operator somewhere here, and this would turn into an incoming scattering state. Okay, so this is in principle the formula that I wanted to show you. And now let me make some comments about it. Yep.
You created something like a local operator in momentum space, right?
Yes.
Should you not do some kind of LSF reduction to go from that to?
Yeah, I mean, I guess in principle, I don't know. I guess in principle, when you take this Fourier transform, you should be careful about doing the LSC correctly. Yeah. So if you want to be very rigorous and write the Hkl kernel rigorously, you will have to apply the LSC reduction formula to this position space operator. But roughly speaking, it's a Fourier transform, right?
Very roughly speaking.
Very roughly speaking. Okay.
But you have to insert, I mean, are you getting a pole at the physical value of momentum? If you just do the Fourier transform without any.
Well, no, that's the thing. You would get a pole unless you use the LSC. Right? You have to act with the LSC reduction formula here to get rid of all those unwanted poles.
Yeah.
Exactly. So yeah, you have to do that carefully. Yeah.
So you also started with a 5 being free, so you have free.
Yes. All of these, I mean, I am using this formula right here. So maybe it's a good time to mention that. So I have built Fock states, which means that at the level of building a scattering state, I have assumed that the theory is free. Okay? Imagine that I wanted now to do something like this. So if I wanted to do to create some scattering amplitude that instead takes Fatef-Coolidge states, then what I will have to do is to use the appropriate formula here for a field that is interacting with part of my Gates field. But this is actually known. I mean, the guys in HKLL, or a subset of HKLL, have papers telling you how you can reconstruct these fields at the boundary.
Is that SPI is a free?
Oh, here. No, no. So what I would say is that in order to build the scattering states, we have used a free theory. However, when we take these operators and we compute a conformal correlator of these operators, the conformal field theory is completely non-trivial, and it doesn't have to be a generalized conformal field theory or anything like that. And the non-trivialities that come in this conformal correlator will result in non-trivial scattering amplitudes in the flat space geometry.
But I'm still confused by this DT integral. So let's take case when all particles are massive. Then I guess you're saying that this DTI integral just localizes, and then can we just take this integral? And
This integral localizes?
Yeah, well, you have this integral DTI, right? So you say, okay, you're not actually taking it from minus infinity to infinity. You're taking it over some small region, which means that probably in some R to infinity limit, you can just take a value at the point. But then it looks like, I think it should reduce to the formula that Schroeder was writing, right?
So in the case, so let me just mention one thing. In the case where all of the operators are massive,
yeah.
Then I expect that to be completely true.
But then, I mean, as they show, there is actually some subtlety with this formula that, I mean, if you, not always that you take, when you take this limit, you actually get a sensible answer. So what's going on?
So actually, let me ask a question to the audience. I mean, does this formula make sense? Joao, or because okay, what I can say is that if you take this equation, it does make sense. Okay, so if I take this equation and I take some operators right here, and I take this conformal correlator and I write it as a Mellin, I write it as an integral over Mellin space, then I can use the large R limit to approximate that integral over Mellin space with a stationary phase approximation. And the saddle of that stationary phase approximation is this point. Okay? So I guess the point I'm making is that this formula reduces, indeed, when all the particles are massive, to the known results written in this paper, which I think that the people speaking this morning agree with.
What happens is that if you take the saddle, sometimes you need to cross the poles, and the contribution of that pole sometimes dominates. So that's how
okay. Okay. Well, I expect that will happen in this calculation, though.
Yeah. So that's what happens.
Okay. Okay.
Sorry, but this in this calculation again, because this formula looks more like position space formula.
It is a position space formula, yes.
I mean, there's only DT.
Yeah, but I think technically, what can go wrong is that, so there you needed to take the complex saddle, when you,
yes,
as Joao was pointing out.
Yeah.
And then again, also when you go to the complex saddle, then if there is some unexpected singularity.
But I would expect those unexpected singularities to appear in the Mellin amplitudes in this correlator, in a correlator of multiple fields. But in the Hkl kernel, I don't think that would happen.
Your formula doesn't have any Mellin amplitude.
No, it does, right? I mean, I can write this guy. This guy is an integral over Mellin space of some Mellin amplitude, and then the kinematic factors or whatever, right? I mean, I could write something like this, and then these guys, I have to evaluate them at these points, which means that now this guy will be a non-trivial, will give me a non-trivial a non-trivial stationary phase approximation calculation, and in principle, well, I checked that for a 2-to-2 scattering, I could reproduce this kind of formulas, for example.
I think the question is, which is the range of momenta or of Mandelson invariant for which your formula is correct, your line is correct? Because from what we learned this morning, in position space, there is some restrictions that you have to be in a given region.
Sorry, those restrictions came from analyticity of the resulting S matrix?
I think in your analysis, it's the same as what Shota said. So the saddle point analysis. It's fine line you have the saddle point. You also have to think about your contour and how many poles you have to cross to get to the saddle point.
I think, though, that should be an issue that appears when you actually compute this formula. I don't think that issue has appeared yet through this kind of logic.
I think at least my understanding is it exactly appears when you go through this manipulation. Because in this formula, there is nothing left to be done. I think we can check explicitly, no? If we take whatever some approximation, with a Witten diagram approximation to this correlator, then was shown a couple hours ago that this limit doesn't make sense in some kinematics, right? It's like S equals 5m squared. Okay, we can show explicitly that's infinity. Yeah.
Okay, I haven't checked that myself. I don't know. So okay, so that aside, I made the comment about how to create FATF Coolidge states. Another comment I should make is, again, the fact that even though I used a free theory to build the scattering states, in principle, the conformal flow theory doesn't need to correspond to a free theory in ADS. And also, the operators appearing here, I could choose all of them to be massless and obtain these Fitzpatrick-Kaplan stuff, or I could choose all of them to be massive and recover these kind of formulas, or I could choose some mixed configuration. So I could choose a bunch of these guys to be massless and a bunch of other ones to be massive, and I could try to obtain the S-matrix amplitude of some mixed process between massless and massive particles, which I think is interesting and should be understood a bit better. All right, so okay, I have given you a formula. Let me give you some checks. So first of all, let me give you some trivial checks. So what happens if in the conformal flow theory I study the trivial correlator? So for example, a conformal flow theory two-point function. So this was done by Xiang before, actually. So say I consider this kind of correlation function. So in the vacuum of my conformal flow theory, I have two operators, O1 and O2, and this is equal to an expression that is fixed by conformal invariance, which is something like this. If I plug this object into that formula there, I perform the smearings and all that stuff, what I end up getting directly is just a momentum-conserving delta function. Here I will get P1 plus P2 because I consider all the operators to be outgoing, but in principle you can consider outgoing and incoming. Same thing is true, sorry, this is under the flat limit. Again, I won't bore you with the three-point function. With the three-point function, it's exactly the same. You can take the three-point function, put it in there, and you will get a momentum-conserving delta function for three momenta. They can be massless, they can be massive, they can be whatever you want. Maybe a less trivial, but it's still completely fixed by symmetry calculation that you can do is that one about conformal blocks. So say we take a conformal block here of one pair of operators exchanging some representation with the other pair. Where here there's a sum over all the states in the representation labeled by alpha. So here there's some representation that is labeled by some conformal dimension alpha, and that should turn into some mass m alpha in the bulk. Whether it's massless or massive, it doesn't matter. Now this object, you can compute it sometimes in conformal flow theories. Pictorially speaking, you have two operators, and they're exchanging a representation with the other two operators. So you're fixing the Casimir here. And in the bulk, they can be computed by geodesic Witten diagrams, which are Witten diagrams where you integrate the vertices over geodesic. So this is a calculation that you can do very explicitly. And if you take the flat limit according to that formula, what you will find is a momentum-conserving delta function with a linear combination of operators so that the momentum is conserved, and then some delta function that fixes the Mandel-Strand variable S. And this makes a lot of sense because we started with an object that is fixed by global conformal invariance and is fixed by fixing the Casimirs of the global conformal symmetry. And we end up with a formula which is fixed by Poincaré symmetry, which is global BMS symmetry, whose Casimir, which is the Mandel-Strand variable S, is fixed by a delta function. So in a sense, like we started with a function that fixes the conformal Casimir, and you end up in a function that fixes the Poincaré Casimir. This had to happen almost trivially. Okay, so These are all examples that I think are very trivial. Let me give you an example that is a bit less trivial in the sense that it doesn't involve the vacuum state. So when I was playing around with this formula, I was looking for an example in which one could test it. And I found these papers from like 1980s or something like that by Tooft and Desser, Jakif, and maybe other people, in which they consider scattering of some particle against a cone. And when I say cone, I mean a conical deficit geometry that is asymptotically flat. And what they found was the following. So say we have a conical deficit geometry, so that I will represent here with a branch cut. And I have some wave that comes this way with momentum P1. What happens is that this wave propagates over this geometry, and it scatters against the geometry. And what ends up happening is that part of the wave completely ignores the cone. So let me use colors, I guess. So this is the wave that completely ignores the existence of the cone. And then there is a part of the wave that scatters away in a spherically symmetric fashion. So that there's some S wave that scatters away from the cone. So these guys, Desser and company, they computed the scattering amplitude associated to this process. And what they found is that the scattering amplitude from P1 to P2 was a momentum conserving delta function. So by the way, this is in, let me be clear, this is in 2+1 dimensions. And what they found is there's a momentum conserving delta function that corresponds to the completely unscattered part of the wave, and then some term that conserves the energy, because energy, like time translation, is still a symmetry of this geometry, but that has some non-trivial profile here with the angle, which was pi over alpha, something like this. This is theta 1 minus theta 2, where thetas are the angles of the momentum. So alpha here is the angle deficit around this cone. So the angle deficit is parameterized by alpha. When alpha goes to 1, the cone disappears. And actually, if you look at this formula, when alpha goes to 1, the sine of pi is 0, and all of this part of the scattering goes away, and you end up in the trivial propagation in a flat geometry.
Do you have some coefficient in front of red delta function?
Yeah, I guess you have to normalize this well. I didn't bother with this stuff. But yeah, you have to do that carefully. Okay, so now what I would like to do is say, okay, well, I mean, this is a non-trivial kind of a scattering problem between a geometry and a particle. Can I obtain an answer like this from a formula like that? And the answer is yes. So as I said before, the CFT state alpha, which is created by this heavy operator with conformal dimension proportional to C, oh, it's right there. Okay, so there is this CFT state that is the heavy operator acting on the vacuum, is dual to a cosmic string in ADS, and it corresponds to a conical deficit geometry in flat space in the large R limit. So I hope that computing correlators in this kind of state results in this kind of formula. So what we would need to compute is the correlator between some operator O1 at some point x1 and some correlator O2 at some point x2 in this conformal field theory state. This is a non-trivial object that you can go ahead and compute in a conformal field theory. The way you can see that it's kind of non-trivial is because the geometrical picture of this correlator is something like this. So there is a cosmic string here, or a conical deficit, or however you want to call it. And then we have some operators here, O1 and O2. And if you compute the propagator associated to this geometry and asymptotic to the boundary, the propagator will contain contributions of particles that don't wind around the deficit, but it will also contain contributions from something winding once or twice, or et cetera, et cetera. And in order to compute this correlator, you actually have to take all of these contributions into account and get a non-trivial expression for this correlator.
Is it different from just completing the Virasoro identity contribution?
It's different. So the Virasoro, the problem here is that a Virasoro block has branch cuts, so it cannot really be an actual correlator, but you can sum over the vacuum Virasoro blocks in all channels. And this is basically what I'm drawing here. These are the different channels for the vacuum block, the holographic computation of a Virasoro vacuum block in the different channels. Okay, so there is different channels because you have a conical deficit, so you can always wind the representation around. Okay, so yeah, this is like an infinite linear combination of Virasoro vacuum blocks. Okay, but I'm not going to write the explicit expression for this guy, but if you take that explicit expression, you replace these locations in the conformal field theory, you perform the smearing, and you spend a fun week, you get this expression. So
And this is massless particles,
you can do both work, yeah.
and this formula works.
And I think that the desert initial calculation was massive, but were you?
Yeah, that's what I was asking.
Yeah, I think the initial calculation was massive, but I think this works for any particle. Okay, so to finish, I just want to say that non-trivial conformal correlators can translate into non-trivial S matrices, and that triggers my curiosity about how much we can learn about the non-trivial structure of flat space, its IR physics, et cetera, from the perspective of conformal field theories. All right, thank you very much. Yep.
So there you just like took the limit of the global conformal block, but if you start from the Virasoro conformal block, do you get something like a BMS block?
That's a very good question. That's something I want to study in the future, indeed. The only thing I can say is that the only case that I have studied is the vacuum block case, which is this kind of case with the deficit. But I agree. I don't know I don't even know how to compute BMS block using BMS symmetry. So that's already a good question on its own. But maybe hints about what their solution is could be studied by taking these flat limits. But I haven't done it. That's a good question.
Yeah, can I ask people if this makes sense, that there should be some formula for mixed massive and massless particles, which is basically for massive particles, it's a purely position space. You just take them whatever according to our prescription, and you don't take any integral. Or for massless particles, I mean, you put them in this bulk point, and there you need to take a Fourier transform, because for massless particles, you need to indicate somehow which is the energy. There you need to take these Fourier transforms. And then if somehow, at least in some kinematics, I mean, the limit will exist, these integrals, this Fourier transform will exist, and then it will be like a mixed massive massless formula. Does that sound reasonable?
I'm not sure why. I mean, this is a mixed massless massive formula.
Yeah, no, it's basically your formula, I guess.
Okay.
All I'm saying is that modification is that for massive particles, you don't really need to take any integrals. You just put them where you want. And,
well, I don't agree,
where
actually.
you want, but where you... And another modification to your formula is that actually you need to be careful with where you are putting them, because sometimes the limit does not exist.
Yeah.
Can you actually address this point? So can you remove the integral if the particles are massive?
I don't think so.
You don't think?
No,
But
I
why?
won't say no because I'm not completely sure given the results that we heard this morning, but from my way of doing things, it almost seems like you need this integral to be there.
But then what, the range of integration matters? Well, that's what I don't understand. If you have an integral, okay, now you didn't write. You're not integrating from minus infinity to infinity because you're saying you're integrating over a small range. You're integrating from some minus t0 to plus t0. So does anything depend on this t0?
As you take the large radius of ADS limit, this t0 should go to infinity. So in other words, you can, just if I swap this limit with this integral, it would make more sense. First, you take the large radius of ADS limit, and then you have to perform this mirroring.
Yeah, but then we know that in some cases you get it.
Well, I mean, the way it works at the level of the computation, the way it has worked when I have done calculations, is that This correlator, you always put it in some kind of integral transform like this guy. You use the large radius of ADS limit to take a saddle point approximation of these things. And then these kind of integrals play around together to give you the momentum conserving delta functions.
I don't understand why you're always appealing to Mellin space formula. Like in principle, correlator is something well-defined thing, unlike Mellin transform. No, well, I know, I heard Joao's talks, but taken it.
Motivation for me to finish.
Yeah, but taken at face value, right?
I feel like you cannot just take this correlator, write it in position space, and take this large radius of ADS limit. Like you always.
That's what.
Yeah, maybe they are better at it than me, but normally I just find infinity get confused and I cannot do anything with it. So I usually have to write it as a Mellin transform or some spectral decomposition of the correlator or something like that, and then approximate the resulting sum or the resulting integral with saddle points. That's usually what happens to me. I'm not sure how to take the large R limits of these kind of guys.
What happens for individual diagrams, you can represent by Mellin amplitude, that we know.
Yeah.
That's how you can see this as -4,
Yeah, that's right. Yeah.
But you have to be careful, right? Because we found this thing, because we find exactly the same saddle point as you found, I think.
In different coordinates, probably, right?
But it's the same saddle point because it's the saddle point that we already knew from the previous data.
You're talking about this saddle point?
Yeah.
Yeah, okay.
So that we find, that's all fine, but now you have to check like, what else. Right?
So what goes wrong, actually? What goes wrong is that the contribution from that saddle point is not the whole story.
Yes.
You have to add more contributions from other points in Mellin space.
Yeah, because you deformed your contour to get there.
Okay, I'm happy with that, yeah.
Okay, let's thank Eliot again.
Thank you.